Hey guys, before we wrap up the unit on gases, I want to go over one last topic related to what we were talking about in class last time we were together, and that's the concept of ideal versus non-ideal gases. So the last time we were together, just to reflect on what we were doing last time in class, if you remember, we were looking at gas variables and the relationship between what happens when you add more gas to a non-flexible container, what happens when you heat a gas in a non-flexible container. We looked at what happens then, what happens when you add more gas to a flexible container, heat gas in a flexible container, and what happens when you reduce the external pressure to a gas in a flexible container. We looked at their independent variables, their dependent variables, and then we talked in depth about direct and indirect, or direct and inverse proportions. And then we looked at what the graph would look like if we were to graph these relationships. And then we spent some time in class going over some math problems using the combined gas law, if you remember, that's found on our reference tables on the last page. The combined gas law, P1 V1 over T1 equals P2 V2 over T2. Keeping in mind that sometimes we got to use this formula down here for temperature, making sure that the temperature is always in Kelvin because it's got to be absolute, no negatives, no zeros. So we did a couple problems where we looked at what happens when you heat, when a gas is put into a bigger container. We saw that the pressure goes down because there's less collisions of the particles with the walls of the container. We looked at an example where a gas was heated, and mathematically we saw that the size of the container got bigger as a result of the gas hitting the walls of the container with greater frequency and with greater force, making the container bigger. We looked at an example of what happens when you throw an aerosol can into a fire. Remember that even though the temperature here is listed in degrees Celsius, down here in the formula we had to convert it to Kelvin. And then depending on the class that you're in, we looked at a couple other problems where we looked at mathematical relationships between pressure, volume, and temperature. You can always go back and look at these on the video and pause it and take a look at the answers. All right, so to wrap up this topic on gases, we have to look at first, real quick, Avogadro's law. So this is letter G in our notes. Avogadro's law, remember, is the amount-volume relationship. Now, we already saw the relationship between amount and volume when we looked at the POGL here in Model 2, Experiment C. As more gas was added to the container, the size of the balloon got bigger because there was more moles of gas. But more importantly, Avogadro stated that if you take equal volumes of gases, that means 2 balloons, 3 balloons, 4 balloons that are the same size, and if they're at the same temperature, so if they're in the same room together, same pressure, the reason they have the same size is because they have the same number of particles. So it doesn't matter if it's helium balloon, filled with air, filled with carbon dioxide, filled with oxygen, filled with nitrogen, doesn't matter. The reason they all have the same size is because they all have the same number of particles. And remember from our discussion in class, the mole box, 1 mole of any gas at STP is going to occupy 22.4 liters. All right, so the big topic of discussion today is ideal versus real gases. So first, let's talk about what the definition of an ideal gas is. It's a theoretical gas, described perfectly by the KMT, kinetic molecular theory. So why is it theoretical? Let's go back in our notes to what the kinetic molecular theory was. A little too far. All right, so the kinetic molecular theory. 2 things that we listed in the kinetic molecular theory that we said is true under normal conditions, but remember under extreme conditions doesn't hold true, was the fact that the distance separating gas particles are relatively large. We agree with that. That's what makes a gas so much more compressible than a solid or a liquid. But the theory states that the volume of the gas particles is assumed to be 0. That means they have no space. That contradicts everything we've talked about in class so far this year, because from our discussions in class, all matter is made up of atoms, and we know that atoms have mass and take up space. So under normal conditions, that works, but we're going to see in a minute that doesn't work under all conditions. And the other point in the theory that works under ordinary conditions is that gas particles exert no force on one another. What that means is that gases don't liquefy, and that's true. I mean, nowhere in the room that you're sitting in right now is there tiny droplets of liquid nitrogen or liquid oxygen just falling from the air, and the reason for that is because the gas particles in the room don't liquefy. But that's not to say that gases don't liquefy. We know that there's liquid nitrogen. We know that dry ice exists, and those things wouldn't exist unless there were attractive forces between the gases. All right, so let's go back to the ideal versus non-ideal conditions. So an ideal gas, theoretical in nature, but there are gases that come close to being perfectly described by this theory, and those are gases that are really small and nonpolar. That means they take up as little space as possible, and they have the weakest attractive forces, and the best two examples are hydrogen and helium. Now, all gases are real gases because they behave ideally under most conditions, but they behave differently under low pressure or low temperature and high pressure. Let's take a look at why that is.
The kinetic molecular theory assumes that ideal gas particles have no volume, although they actually do have volume. As you learned earlier, their volume is just so small compared to the space between particles that at low pressures, their volume is not significant. At high pressures, however, the particles of gas are pushed so close together that their volume can no longer be assumed to be zero. This is one way that real gases deviate from the ideal gases. Another assumption that is not valid for real gases is that gas particles do not attract each other. As you probably know, all gases can be turned into liquids at low enough temperatures. Particles in the gas phase are attracted to each other, but the gas particles are moving so fast that these attractive forces are not significant. When the temperature of the gas particles is decreased, the gas particles slow down, and the attractions between them become significant. At low enough temperatures, the attraction between gas particles becomes so great that a liquid forms. The attractions between real gases cause them to deviate from the ideal gas law. Although the kinetic molecular theory makes two false assumptions, it is still an excellent and simple model that accurately describes and explains real gases under standard conditions.
All right, so this next summary table isn't in your notes, but let's make one. And let's summarize what we saw there as it relates to ideal versus non-ideal conditions and gases. So let's start with the gases that we looked at. So an ideal gas is theoretical in nature, meaning it takes up no space and has no attractive forces. So the closest are going to be small, nonpolar gases with weak IMFs. So we're talking about gases like helium and hydrogen. On the other hand, large polar gases with strong IMFs are going to be very non-ideal. So what are we looking at? We're looking at things like SF6, that's really big. That's the gas that makes your voice really low. And something like carbon dioxide. Carbon dioxide is no good because it's really big. Gases that have really strong attractive forces like NH3 or HCl. Those are polar molecules. They have really strong attractive forces. No good. Don't behave ideally. What about conditions? The best conditions are the ones that keep gas particles spread far apart. Now we saw in the video that The things that were non-ideal, the opposite is ideal. So we're talking about high temperature and low pressure. High temperature and low pressure is going to keep the gas particles spread as far apart from one another as possible. Now, when the gas particles get close to one another, they stop behaving ideally, and then they get real. So we're talking low temperature. That's when they're going to liquefy. So we're talking less than 0 degrees Celsius. And high pressure means greater than 1 atmosphere of pressure. Those are no good. All right. So now you guys got everything you need for the Castle Learning assignment that's due tomorrow and the quiz that's due on Wednesday. And then on Thursday, we'll pick it up with liquids and solids.